Okay. Okay, there's 25.
Can you give me permission to?
How do I do that? More. I have no idea how to do that. Make co-host. Can you record it now?
Yep.
Cool. Okay. So, welcome to Code 2121. I'm Andrew Butler. I am an associate and a lead computational designer at Cox Architecture. I've been teaching in computational design for probably like six years now, and this is maybe the third or fourth time I've taught this particular course. It's been shaken up a little bit, like usual. It seems like every year the code student cohort are guinea pigs in one way or another, and you guys are guinea pigs because I've never taught this course remotely, and as well I've never taught this course with a 3-hour time slot, so bear with me. I'm going to try and make this as good a course as possible for you. Also, normally I get to meet all of you a term previously, so I used to teach 1240. It was COVID that kind of got in the way of all of that. All the sessional stuff got let go last year. So I believe you all did that with Christina last term. Is that right?
I guess yes.
And then Christina kind of, she stopped just before the end, and then maybe Daniel, you took over. Is that right?
They both did it at the same time. They both took a class each.
Oh, okay. Yeah. They were tutors.
Yeah.
Right.
Yeah.
Okay.
They were both tutoring.
All good. Okay. So
10:06.
Pardon?
Wait, is my mic muted?
No.
Fuck me.
All good, Declan. Don't worry. We're not. This isn't. This is a fairly relaxed class. So, I need to know. I need to know what you guys understand in computational design. I need to know what you like, how you approach problems with Grasshopper and algorithms and parametrics and all of that. And so this particular course is going to be, in a way, going over what you guys have learnt from previous classes, and hopefully it'll be an opportunity for you to when I say relearn, so relearn those techniques, but then applying them to your designs, right? So rather than it just being for example, you've probably done finger jointing in 1150. The concepts behind finger jointing really should work to be able to produce trusses. And so rather than just sort of saying, okay, here's the script for producing trusses, or here's the script for producing finger joints, I want to make sure you guys know how to take the techniques and apply them to whatever problems are put in front of you. So I'm not here. This course is not here to blow your minds. Okay. It's here we're here to sort of take a breath, have a bit of relax, and actually just assess everything that's happening with computational design that's kind of been crammed into your heads for the last 2/3 of the year, and produce something really nice. Okay, we're gonna make something that sounds really daunting from the beginning, but it's like, if we approach it the right way, then it should be really simple, and relaxing exercise that cements all of this stuff in your minds. The other thing is, I do have to teach you something though, rather than just go over previous things. And so we're going to be learning about structural engineering. We're not going to be learning how to be structural engineers, or otherwise you'd all be doing a structural engineering course. But rather we'll be learning about how to communicate with them, the basics and the foundation knowledge to work with a structural engineer. And we're also going to be working with various different Grasshopper tools that almost function like structural engineers. One thing I just want to point out: Will is a computational design grad. He worked with me at Cox for 2 years?
Yeah, about 2 years old.
About 2 years, and he's only just recently left us to go work for a structural engineer. There used to only be like a few people, coming out of this degree that used to go work with engineers, and it's getting more. There's more and more and more. So this is a decent course to sort of like ground yourself in, and can potentially consider getting into that career, because even though Will's been hired by a fairly large, standard practice of Mott MacDonald, they're a global practice. Will doesn't have an engineering degree, and yet they still think that he has some value for them. So that's think of that as maybe a little role model for some of you. Also, I understand another thing is this class has got quite a lot of 1 year students. So that's people coming from the interiors, the architecture, and the industrial design degrees. Is that correct? Usually I've only had about 1 or 2 students in the class, and I think there's like maybe 6 to 10.
I guess we got a landscape student.
Oh, and a landscape student. Okay. Is that you?
No, it's a friend of mine.
Okay. Like, just looking through, I can see, not to, be too, pointing people out, but I can see Timothy, is Anthony Franco?
Yep.
Is that is that industrial design?
Yeah, there's quite a few of us.
There's quite a few.
Yeah,
right?
Industrial design and architecture and
Yep.
interior. There's quite a few of us.
Yeah, and the thing is, you guys have all completed like 3 to 4 year degrees, right?
Yep.
Which means you've probably learnt some of this stuff already. I think, like, the architecture degree should, in theory, I haven't done it at UNSW, but it should kind of cover some of these concepts. So just note, I understand that there might be some double ups here, but I guess it's good to recover this stuff, right?
Yep.
Cool.
Yeah.
I guess, and the other thing is, like, I work in an architecture firm. A lot of this stuff that we'll be focusing on this term has an architectural relationship, but as with anything structural engineering wise, it's technically applicable at any scale. So hence why I think you guys are, learning about loads and live loads and stuff like that might end up doubling up. So sorry about that. Just let me know, give me feedback if things are, being a bit too repetitive for you, it's just, so that way I can maybe adapt as we need to. Okay, I'm sick of looking at this guy having his mind blown, so let's go. So what are structures? Structures, they can be identified as, before we do this one last thing, I need you guys to take notes during this lecture. I know for some of you it might not be a natural thing to do, because it certainly isn't for me. But part of your first assignment requires a glossary to be developed from some of these lectures and stuff that you've been learning in class. So just to save you time, it's worth taking notes so that you can attach those notes to your first assignment. Okay? So you've probably all opened up Notepad or Word or whatever, and just keep along and write this stuff down. Okay. What are structures? A structure can be identified as any assemblage of materials which is intended to sustain loads. So what that means is almost everything that we have around us is actually structures. All living creatures have some form of structure, from membrane like barriers, tension structures, to bones, which are like beam-like structures, to shells, so shell structures, you know. So some of the stuff that we'll be looking at with structures is almost like it is second nature to us normally, and it's really about like sitting down and looking at you know, things that we sort of take for granted and trying to understand them. So structural engineering in particular, is the applied science of predicting how a structure will behave under given loads. Engineers use many abstractions and assumptions to simplify the world around us and to approximate the behavior of a structure. In structural engineering, we deal predominantly with what is known as statics, and statics is the branch of mechanics concerned with bodies at rest and forces in equilibrium. And we'll talk about equilibrium in a moment. So when we talk about the use of many abstractions and assumptions, spelling mistake there, we're referring to the fact that if you sit down and actually try and solve a structural problem, you know, predicting whether or not a building will stand up, whether or not a tower will fall over, etc., it would take us quite a long time to actually replicate that scenario one-to-one, you know, with all the materials and everything, all the atoms placed. It's just too much information. You might as well just let the building fall down. So rather, there are much simpler understandings of the world that can be abstracted into formulas and models, and we can use those models to have a fairly good understanding of what will happen. And that's generally, you know, I think 100% of the engineers' workload is actually just working with those abstractions. It's amazing how you could potentially give an engineer at a particular time a problem, and they'll just sit down and do like 5 maths equations and say whether or not it will work or won't work. And they've got like a 90% correct answer, basically. So we're not engineers, but we will always be communicating with engineers, and engineers will even say that they're not very good to communicate with. Like, if there is one trait that best defines an engineer, it's the ability to concentrate on one thing to the complete exclusion of everything else. This sometimes causes engineers to be pronounced dead prematurely. What that really means is, if I'm working with a structural engineer, the only thing that they're really focusing on is the structure. And the only thing they care about is the structure. And depending on which industry a computational designer might get into, be it architecture or civil engineering or interior design, whatever, the designer is in a way the nucleus of trying to coordinate a bunch of different consultants, and they need to understand what the structural implications are for their design. But at the same time, there's another engineer that is purely focused on making sure that there's air getting into a room. There's mechanical engineers, or your hydraulic engineers, or your fire engineers, the people that are making sure that the fire sprinklers are placed in a safe manner, so that if there is a fire, that the people are safe. Now, some of those things are going to collide with each other, and being able and coordinating that is it's a job. It's tricky, and people get paid to do it. But what else happens is sometimes that clash exists between the designer and the engineer, rather than engineers and engineers, and you end up with a lot of architects who work in a top-down manner, wanting a particular outcome, but that outcome isn't actually feasible structurally, and so you end up needing to have a conversation about how these things need to be achieved. So we're going to be using software this term called Karumba, which in a way is kind of like that really rigid, single-minded way of thinking that an engineer might be, because it's software. It wants to think in a certain way. Working with this software is very similar to actually working with an engineer, other than having that face, because that software needs inputs into it that are very hard to break. You have to work to them very specifically. So that's one of the focuses we've got this term. So part of communication with the engineer is vocabulary. We need to learn what a load is. A load is any force, either externally or internally generated, which affects a structure. Dead loads are loads which are likely to be permanently present. So a good example of that is, the actual structure itself. Like if you make a floor out of concrete, the concrete has some weight, and that weight exerts a dead load on itself. Or live loads, which may or may not exist or be transient in nature. And a really short example of that is humans, right? Humans aren't always permanently in a building, except for maybe during COVID. And so we have to consider that the weight of a human and the potential loads associated with it can fluctuate. Equilibrium, something I mentioned earlier. When summing all forces about any given point, the sum of all the forces must equal 0 to prevent rigid body motion, and we'll get into what that means in a further slide. But it just basically means a balanced outcome. Material versus structure. Material is typically a collection of molecules arranged in a specific way with associated properties such as density, stiffness, strength, etc. So whenever someone is referring to a material in structural engineering, they're potentially referring to whether or not the thing is mild steel, is it timber, is it concrete, is it reinforced concrete. All of those things have certain properties. And then a structure is typically a collection or arrangement of those materials capable of resisting an applied load. So referring to those dead loads or live loads above. Many things can be considered as both materials or structures depending on how closely you are looking at them. So for example, I mentioned before reinforced concrete. Reinforced concrete is concrete, but it's got steel rods running through it. So it's two separate materials, and they exist in a structure because it's two materials in a structure. But when we do analysis on a building, it's not necessary to think of those two things as separate. We can think of them as one and the same material that has a certain type of property. You could hone in on graphite, which is the stuff that's in pencils. That is made up of carbon, and it is made in a certain structure that gives it its properties. And we can zoom out and potentially, think of a whole floor or a whole girder of different elements in a mega structure, and think of that as just a single material. So a lot of this stuff is quite scalable. And then we have elastic versus plastic behavior. Elastic behavior, this is when I need some of my pasta. Okay, so everyone can see my pasta. Elastic behavior is when a load is applied to a structure and then removed, the structure returns to its original shape and size. So for example, with this pasta, you can see it's quite elastic at the moment. I can apply loads to it and it bends, but it comes back to its original shape as I need it, and there's a bunch of loads being applied. And then plastic behavior is when a load is applied to a structure and then removed, the structure maintains a degree of deformation. So in this case, it failed, but actually I can't actually get this thing to be plastic. What else could I do? Okay, you can see the spring of this book. If I bend the spring maintains some of the deformation that's been applied. So that's plastic behavior. Cool? So,
wait a second. Are you trying to use your camera to show us something, or?
Oh, you can't see my camera?
Yeah.
I can see it, Andrew.
I can see it.
I can see him too.
Makes this really.
Can you see? You can't see me at all?
I can see your. I can see your screen.
Can you see me now?
Nope. I'm trying to figure out what is happening.
There should be like a little, sort of floating bar potentially. Have you got a? Actually, sorry. From your perspective, there's different view options.
Okay.
You can see me now?
Yeah, I can see you now.
Okay. Here's the pasta. Actually, I need
I can see
more
your
of it.
pasta. I can see your pasta.
Excellent. Here's the pasta. It's floppy. Right. As in, I'm exerting loads to it, but then when I let go of those loads, the pasta, it goes back into its original shape. Yeah?
Yeah.
That's elastic?
I understand. Yeah, I understand the entire thing.
Cool,
I
excellent.
studied it earlier, so.
No worries. Okay. So, the designer, the engineer, and the computational designer. A good engineer will try to understand what a designer is trying to achieve and develop appropriate engineering solutions. A good designer will understand the principles of engineering and the concepts of how the structure is behaving, and it seems like my N is going nuts when I've been typing this, incorporate them into the design. Now, this wasn't written by me, this is written by an engineer, and I just want to point out, you can see here, a good engineer will try to understand what a designer is trying to achieve, whilst they've put in here, a good designer will understand the principles of engineering. So they've almost written this in a way which is making it out to be that the thing that a designer is trying to achieve is something that you isn't, it might not be possible to actually understand it, whilst we've got some engineering principles that are quite fixed, and so if you talk to an engineer in any part of the world, they're going to be using that same scientific grounding to what's being understood. Now, we're not just going to be designers, we're going to be computational designers, and they're going to be I think they're going to be a little bit different when it comes to working with an engineer and also working as a designer, because not only does a good computational designer understand the principles of engineering and the concepts of how structures are behaving, and also understanding what they want to achieve as a designer, but they're also capable and of understanding a process of how designs are formulated, and can inject this understanding of principles of engineering, so that those principles are actually embedded in the design script, in the algorithm, in whatever, so that the outcome is always going to be satisfactory, rather than there having to be that to and fro. And so what we end up finding is you get the engineer kind of eyeing the computational designers more now than the regular designers. Some random person's just walked into our office. Oh, okay. Is it work? Okay, cool. Okay. So concepts of mass and loading. The difference between mass and weight. So we're going to go back to high school physics a little bit. I'm going to imagine that some of you haven't done high school physics. But if you all have, then we can stop talking about this now. But usually what happens is with engineers, they use the International System of Units, which is a tiny bit different to what usually like architects and maybe industrial designers might be using. And the real big difference is the distance units. So they use mass in kilograms, distance in meters, time in seconds when they work with velocity. Because they're using distance as meters and time in seconds, their velocity is recorded in meters per second. And then acceleration is meters per second squared. And this is the big one. This is probably the one that a lot of you are not familiar with, and that's force, which is measured in newtons. So for those of you who don't know, architects and industrial designers, you guys have probably been taught to work in millimeters. Is that right?
Yeah.
Yeah. I do too. I prefer mils. But whenever we send anything to a structural engineer, they will convert that to meters to be able to do any of their analysis. It's interesting because we don't, even though we work in millimeters, we don't work in millimeters when we talk about area, right? It's not like we say 1,000,000 square millimeters. We say 1 square meter, right?
That's true.
Yeah. So we do have to sort of get into this unit conversion thing when we start working with structures. So force, which is mass times acceleration, is very similar. It's actually the same as weight, which is mass times gravity. So this force in newtons is different to mass in kilograms. Okay, so how do I get? Yeah, we'll talk about it like this. So we weigh something on Earth, a different value to how much we weigh in space versus how much we weigh on the moon or wherever. The weight is something to do with gravity, and gravity has something to do with mass, and mass is something that we have no matter where we are in the universe. Mass becomes really okay, so if I said like I'm 100 kilograms, for example, that is something that matters, like in terms of weight. Something matters when it comes to dead loads, in terms of, okay, I'm exerting 100 kilograms worth of force on a building, But that mass that I have is also important when it comes to wind loads or when it comes to other humans trying to interact with me. So if a human comes over and pushes me, it doesn't matter how much I weigh. What matters is what my mass is. So gravity on Earth is 9.81 meters per second squared, or meters per second per second. We'll just round that up to 10 for any calculations that we're doing from now on. And the gravity on the moon is 1.6 meters per second per second. So a person with a mass of 100 kilograms is on Earth. How much do they weigh? Can anyone have a guess? You know, this one's a really easy question to answer.
981 Newton.
Yes, good. Okay, you answered in newtons, which is great. So you know, normally, you know, regular lay person, you know, just on day-to-day working, we would say, okay, they weigh 100 kilograms, right? But just remember, mass is different to weight, and weight really should be measured in newtons. So
Yes.
you said 980 newtons.
981 newtons.
Yep.
Oh, it's just 9.81.
Yep, and then the same formula would apply with the moon. So we'd get 160 newtons on the moon. One thing we need to simplify right now is, you know, 981. Let's just round that up to 1,000. A lot of the forces that we'll be seeing in structural engineering are going to be really big. Like a newton is quite a small force. So we want to think of, we really want to work in kilonewtons, so that 1,000 newtons equates to 1,000 newtons or 1 kilonewton. Cool? So this kilonewtons is just referring to 1,000 newtons, or in a layperson's thinking, 1,000 kilograms. Sorry.
I think-
guess, should we? You go.
Go on.
You go.
Oh wait, okay. Oh, what I was gonna say is a good way of thinking of like when you're weighing anything is trying to think of the reverse. Like, so whenever you weigh something, you got to think that you have the force applying on
Yep.
that thing that you're weighing. So
You're talking
you
about
have
with a
the weight-
scale, with a scale, right?
Yeah, with a scale. Yeah, with a scale. So you have like that the actual weight, but then you just have the force applying onto them.
Yep.
So because I did physics, so it's a bit more easy for me to understand.
Yep. So what you're saying, Edward, is, you know, if we took any object, let's say we just took like a kilogram of flour, and we put that on a kitchen scale, what's actually happening is there's a spring and a various sensor in that scale that is being compressed by the flour being pulled towards Earth by gravity, right?
Yeah.
And so what we're actually measuring when we measure weight with a scale is we're measuring the force that is being exerted on the sensors there.
Yeah.
And then by getting that force, we can make an assumption of the mass of that object.
Mhm.
Yeah?
Yeah.
Okay. Excellent.
Let's say something more scientific. The mass, goes through some bit relativity. Yes. According to Einstein's theory, mass is actually a property of an object. So, the property of an object means it is a constant. So, if you don't chop it to any other pieces, it's always going to be maintained in the same volume. But the weight will actually change during, if you shift this object from one gravitational field to another, then the gravitational column itself changes, so
Yes,
the weight itself
yep.
changes.
But I think the reason mass matters, because usually most of the work that we're going to be doing, 99.9% of us are going to be doing structural work on Earth, right? So it's not like, gravity is going to change. Like, it's not likely to change. Hopefully it doesn't change. But
Slightly
yeah. Hopefully. But the thing is, what mass isn't just something that matters when it comes to dead loads, right? It doesn't just matter for gravity. Okay, mass also matters for whether or not wind can push something, or whether or not a human can come and push something, or a vehicle crashes into your structure. When a vehicle crashes in, we don't care about gravity, we care about the mass of the objects that are colliding with each other.
And also friction as well on the road.
Sure. Yes. Yeah.
There's a lot of things like they can still. Yeah.
Let's. We want to. We're taking this. Sorry, I don't. Sorry to interrupt, but we want to think about this just really simply. Okay.
Okay. Yeah. Sure,
Okay.
sorry.
Because we can. Yeah. We can totally get. Do you remember what I was talking about before? We're talking about abstractions, right? So you're right. There's a billion different little forces happening when a vehicle crashes into a building. We could think about the friction, we could think about the thermal properties, we can think about all of that, but they're only 1% of the problem, right? The main problem is that big mass colliding with your building, right? So we can just abstract away the reality of all of that itty-bitty scientific mess. Just get rid of it, because if you think about it, and if we actually try and recreate it in the computer, if you actually want to put in, what is the friction that the tires are having with the road, which then determines the velocity of the vehicle, we can forget that. We can round the velocity to whatever, to be, 3.6 meters per second. And we can say this is the 1,000 kilonewtons of force that are being applied, and we can do that work there. So I'm just for Edward and Ding Wen and anyone else thinking similarly, just take a step back. We want to be able to write all of these formulas down as 3-line formulas, let's say. Yeah?
Yeah, sorry. I was
It's
just
all good.
complicating.
Yeah.
It's just like my kind of.
It's good.
Physics
No.
knowledge coming back.
It's really interesting. People can really get into that, the itty bittiness of it, and that's great. But that's not what we're going to do in this course. And I encourage you, if you're really interested in that, get into it and go for it. But it's not what we're going to tackle with these lectures. Okay.
Yeah, sure, easy.
Cool. Okay, so abstractions, right? This is actually perfect. So when we think about forces, we want to abstract them down into really simple concepts. And so, if I take this pasta and think about the load that's getting applied to it, I don't really want to. I don't want to think about. I just lost some pasta into my keyboard, and that's going to jam in a second.
That happened.
I'll get it later. That finger load that I've just applied to it, rather than trying to compute all the little atoms and their electromagnetic relationships with the pasta, to be able to actually work out, all the different loads that are getting applied, we can abstract this all down into point loads, UDLs, or that's universal distribution line loads, or line loads, and pressures. Sorry. So that works very similarly in the same way that we sort of evolve geometry. So if you take a point, which is point is 0-dimensional object, and we add a dimension to that. So if we put points in a row, we end up with a line. And if we take a line and we move that in another direction, over and over again, then we end up with a surface, right? So we can think of point loads as a point of force, a line load, which is just a force, a point load that's been distributed over a line, and then a pressure, which is something associated with a surface, is just a line load that's been then distributed over that surface. So those are measured in kilonewtons as a point load, kilonewtons per meter, so that's that's spread out over that line, and then kilonewtons spread over meters squared, so over a surface. Or just to simplify saying kilonewtons per meter squared, we can also refer to pressures as pascals or kilopascals. A pascal is 1 newton per square meter, and there in this little diagram in the background, there's a square meter, and there's a newton standing in that square meter, so that's 1 pascal. Cool. So I'm going to ask someone other than Dingwen or Edward to answer some of these questions. There's a 1 kilonewton person that we measured earlier on Earth. They're going to be, if they stand at a single point, that's going to be a 1 kilonewton point load. So if that 1 kilonewton person on Earth, who's 2 meters tall, we'll just say, we're abstracting, we're rounding up, they're 2 meters tall and they're lying down, what's their line load force? And then the 1 kilonewton person on Earth stands on a stiff weightless platform, which is about 2 meters by 2 meters. What's the pressure exerted under that platform? So does anyone, if we just look back on this, look at the unit of line load. It's kilonewtons per meter, right? Think of that as just a mathematical formula. If we had 1 kilonewton that's being spread out over 2 meters, what's the line load force being applied at that zone, along that line?
Is it 2?
Is it? So if I had the number 1 and the number 2, what am I doing to those two to get that answer? We're timesing them, right?
Yep.
So it's not 2, because that would mean
0.5.
yes, we're dividing. We're doing the opposite, Timothy.
I see.
Yeah, so it's 0.5 kilonewtons per meter. Thank you, Zinyi. And so if you think the same way, what would be the pressure applied over 2 meters by 2 meters?
A quarter.
Yeah, yep. And what's the unit?
Kilopascal.
Yep, 0.25 kilopascals, right?
Yeah.
Yep, perfect. Or, instead of kilopascals, we could also say kilonewtons per square meter. And look at that. You got it right. 1 kilonewton divided by 2 is 0.5 kilonewtons per meter. And 1 kilonewton divided by 2 is 0.25 kilopascals. Cool. So I know. So look, sometimes we're gonna ask you guys questions in lectures, and it's gonna seem like they're trick questions, right? But they're actually really simple, questions to just make sure that you guys are understanding this stuff. There's no point in trying to trick you guys. Okay. So good job. Okay. So dead loads. If I have a block of concrete on my structure, that block of concrete is going to be exerting a dead load force, and we can get that force. We can work that out by checking its volume and comparing that volume with its density, and volume times density will give you its mass, and that will then tell us what its how many kilonewtons it will be exerting, and so on and so forth. And we can work out if that's a point. We can say if it's a point load, if it's a line load, if it's a pressure. But there are other loads that get applied to buildings, and I mentioned some before. We have wind loads on buildings. Those are actually very important loads to be considering with high density buildings in Sydney. We have seismic loads. I know some of you might be in China. China has is a much more active seismic region than Australia, so it matters quite a lot to understand, you know, this live load that's going to be applied to that building. Snow and ice, they build up on our roofs, and they apply weights on roofs that you weren't really expecting them to be, especially, you know, as an Australian, we don't really think about snow. Thermal loads, so if you're working on a transport job, the railway lines are made of metal, and when they get hot, they expand, and as they expand, they push into each other, and that is applying a load. You end up with buckling, and, you know, the thermal loads have basically killed quite a lot of people in the past. A lot of train accidents are caused by it. Settlement, so that's you know, a much gentler version of what a seismic load is, where the earth moves, and the building you've designed has effectively shifted. Settlement loads, they affect bridges. It affects any very large buildings, so buildings that, you know, extend beyond a certain point. But you've probably all seen cracked plaster walls in some Australian houses, and that's just because, you know, part of the landscape for that has moved, and the house has basically been pulled apart or twisted. And then impact loads, so, you know, that's vehicles driving into your structure. There's quite a lot. We've got to think about quite a lot. Here is a dynamic load from the 1940s.
Tacoma Bridge, Washington, opened only a few months ago.
Okay, come on, YouTube.
Twilio is the leading customer engagement platform, enabling you to reach and engage your customers on...
A few months ago, was built at a cost of over...
So this is Tacoma Bridge from the 1940s. It didn't last very long.
Washington, opened only a few months ago, was built at a cost of over $6 million.
Can you guys hear it? Can you guys hear the audio?
No.
Okay.
No.
I've got this like tinny old guy from the 40s. He's like, Tacoma Bridge, blah blah blah. How do I make you guys?
If you click at the top, there should be like 3 dots.
Yeah.
There should be a share sound option.
There is. Here we go. Thank you, Amanda.
Classic tapes that bridge,
Can you hear it now?
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's 3rd largest suspension bridge.
So this is a resonance frequency load. So the wind is traveling over the bridge, and it's just been designed in a way that...
mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
And so that particular live load wasn't considered in the design, and you end up with catastrophic failure. Does anyone here like dogs? I know Amanda likes cats.
Yeah, I have a dog.
Okay, well, there's bad news at the end of this story.
Finally,
no.
the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Fortunately, the only casualty were cars and a dog.
Wow.
Apparently, someone went to go get the dog. They tried to go save the dog, and the dog was scared of them, and like tried biting them. So they did try to save the dog.
Okay, fair enough then, but yeah.
At least
Yes,
they
it is what
tried.
it is.
Pardon?
Yeah.
At least they tried.
At least they tried, but it's still, you know, it should be unfortunately, not fortunately. So, you would have noticed something there, that building that we're quite used to thinking of buildings as these like really rigid things. You know, they're fixed, and if a human came along and tried to push it or move it, it's not going to bend. but actually, most of the structures that we have, like that we're looking at, we're looking at forces that actually, when they're applied to them, those buildings do actually bend and warp and they have elasticity. Like that bridge had enough elasticity to be able to almost like do this, right? Even though it was made of concrete and steel, it was doing this. It was only until it got too strong that it broke, right? So I'll mention this late, like in a later slide, but everything has to have some kind of like elasticity to be able to actually work as a material with structure. So this is just a really good example of being able to see it working. So sorry. Okay, this lecture is going to go a little bit longer because I've been talking too much, but we'll get through it. Okay, so why do structures carry loads? Equilibrium basically states, like equilibrium, the concept of that object at rest. Newton's third law is when in equilibrium, every action has an equal and opposite reaction. Therefore, unless an unbalanced force exists on an object, it will be in equilibrium. So in space, if I throw an object, let's say I throw a spanner in space, and we ignore the fact that gravity is, infinite, for those of you who want to get into that physics side of it, but let's say there's no forces on it, that object will just travel in a straight line forever and ever and ever. It needs to have another force applied to it for it to change direction. And so, if I have an object sitting in space, there is an equal and opposite reaction to this pasta to stop it from falling through my hand, right? So my hand is exerting force on that. But Robert Hooke's law and springs, sorry, hang on, I'm just going to cough this thing out. Robert Hooke's law with springs is kind of the thing that helps prove everything, which is every solid changes shape when a mechanical force is applied to it. It is the change in shape which allows the solid to push back. So what that means is, and we'll just keep using pasta. So as I put pressure on an object, what happens is every object, every single one, concrete, steel, something that's really rigid, it actually deforms. And the way it deforms, and I'll see if I can get this pasta to do it the way that I need it to. The way it deforms is it squishes out proportionally to the force that is pushing down on it. And what happens is the molecules in that object are being pulled apart, and they don't want to be pulled apart, and so they basically resist that, and they pull back on each other, and that is the thing that is then pushing back on that force being applied. The same applies, if I pull on something, then the molecules get stretched and pulled in to each other, and they're pushing back on each other. They want to be at a certain distance, and so that force of those molecules trying to push themselves back is the thing that is resisting that pulling tension force. So if I hang on a weight at the end of a bungee cord, the bungee cord will stretch proportional to the weight applied. So because bungee cords are rubber and they're sort of designed to do that. So the bungee cord starts really fat, and as we fall, it gets thinner and thinner and thinner. When I climb the stairs of a tall building, the building itself will, in a very, very small manner, contract to resist the load of my weight. So that's happening to all of you right now. The force that you're applying to whatever floor you're sitting on, that floor is actually contracting just the tiniest amount. And if I hang on the end of a tree branch, the branch will deflect to support my weight. On a molecular level, the chemical bonds between atoms are very strong, so stretching of a material is only possible by stretching or compressing many millions of bonds. And it's the strength of those bonds which defines effectively the properties of those objects. So ut tensio sic vis, which stands for as the extension, so the force, Hooks undertook a variety of experiments and found that up to a point of load, most materials deformed proportionally to an applied load, where the formula equals F equals K times X, or force equals stiffness times extension. Cool? Stiffness as a property of a structure is both related to its geometry and the material properties, so we'll get into that in a bit. But the stiffness of this pasta is effectively defined by the flour molecules that make up the pasta, right? And okay, so the final part, and this is a really important one, designing for safety. What loads do we design for in our structures, and how do we design our structures to resist these loads? So we usually are designing for people. We want to make sure people are safe as a priority. And so the Australian Standards 1170.1 designates the minimum loads that a structure must be able to resist. Now, most of you don't probably know this, but Australian standards are, they're a document that you actually have to pay for. So, this one's $55. Actually, look at that, just jumped up to $83 because it probably knows I'm in New South Wales. So don't bother to go get this because you're going to be spending money on something you probably don't need until you actually move into your industry. If you guys want to see a copy of this, I can try and scab one off of Cox and make it available, but just keep it secret. Okay? Cool. But part of that clarifies a few things. When we're designing, so we've got Newton now. Newton's now he's not going to be 1 Newton anymore. He's 1,000 newtons or 1 kilonewton. So each of these little newtons is 1 kilonewton. We typically design for these pressures on these floors. So a typical house live load design value is designing for 1.5 kilopascals. And that's the equivalent to, I think it's 8, 1, 2, 3, 4, 5, 6, 7, 8. It's roughly 8 people standing in a 1 by 1 square meter surface. A typical office live load, we're looking at 3 kilopascals. So there's about 16 people there. And we're not just now thinking about people, we're thinking about the fact that there's potentially like different types of furniture like cabinets and bookcases and stuff like that that might be placed on that floor, and that's why we have to consider this as a live load. A typical museum live load would be 4, because there's the potential of very heavy ancient objects getting placed in specific areas. And see, we're getting almost completely unreasonable social distancing factors now in that one square meter. A typical shopping mall, I think that's getting up to about 25 people all in 1 square meter. That's 5 kilopascals. And then a typical heavy plant room is I think it's about 43 people. At 7.5 kilopascals. Typical heavy plant rooms. So these are the large air conditioning units for buildings, generators, electrical capacitors and distributors in buildings. They're very, very heavy pieces of equipment, and we have to consider that they're going to be exerting quite a lot of force on that floor. There is a table of with more information about how the different weights. I've got this copy like available right now, but it's awful to read. You can see like it's all pixelated. So I'm going to get a better version of that and make it available to you on Moodle. But if I just try and read into that here, you can see self-contained dwellings, general areas, private kitchens, and laundries. That comes out to 1.5 kilopascals. So that's referring back to that that typical house, 1.5 kilopascals. So, structural engineers design for the principle of strong columns, weak beams. So this means the safety factors are typically higher for columns and beams. What is a safety factor? It's this number here, but there is a separate safety factor that engineers use. They basically increase these numbers by a factor of 20 or 50%. So, they might make their columns 50% stronger than what they might need to be, and they'll make their beams 20% stronger than what they might need to be, just in case. You're always doing a little bit more just in case. Elements which behave in a ductile manner, ductile meaning able to be deformed without losing toughness, so elastic. In a ductile manner during overload can have a lower safety factor than those which behave in a brittle manner, and ductile materials are able to undergo large plastic strains before they break, while brittle materials can only sustain small plastic strains until they break. So, examples of ductile materials versus brittle materials. Ductile materials are materials like steel, conventionally reinforced concrete, most plastics, spider silk, plasticine, putty, chewing gum. It's basically a material that can be bent, and after bending it, it still maintains its strength, right? So if you took a metal ruler, for example, and bent it, it's not like immediately that material that is going to snap soon. You could bend it back, and it's still got its material strengths. Brittle materials are materials like glass, plain concrete, ceramics, chalk and rock, bones and teeth, stuff like that. And then in between, you end up with timber. Timber's a really interesting one because, depending on the species of timber and how it's treated, it could be ductile or brittle. Over-reinforced concrete, which is concrete that has way more steel in it than what the concrete can support, ends up sort of end up being half ductile, half brittle. And I think pasta is a little bit ductile, but yeah, it's you can bend it a little bit and then it snaps. So it's kind of like more on the brittle side of this grid. Often ductile materials have a low modulus of elasticity, meaning material stiffness when compared to brittle materials. So if I took a block of concrete or a sheet of concrete and just applied any form of bending, it doesn't have any elasticity. Some materials, such as steel, however, exhibit both high material stiffness and high ductility, making it perfect for building with. Many brittle materials have a high strength in compression and a low strength in tension. So that's generally why we see rocks and concrete being used as compressive elements like foundations, or in archways and stuff like that. Limit state design, ultimate limit state. So when engineers design, they can design to either the ultimate limit state and or the serviceability limit state. The ultimate limit state is basically designing something for its sole purpose. So it's used for designing bridges and stuff like that. It's designing for strength and stability, factoring loading and material properties to give required factor of safety. Serviceability limit states are more pointed towards buildings that humans might exist in. So designing for deflections and predicting occupant comfort. So if you're in a 30-story tower and you're at the very top, remember how I mentioned buildings, they're going to have that flexibility. Towers, tall towers actually sway in the wind, and they can safely sway in the wind to an extent that makes people worried. So if you're standing at the top of a 30-story tower and it's swaying, that person is actually uncomfortable in that tower, and generally the engineers have to design, over stiffen that tower, not just for safety's sake, but also people's comfort. And generally when that happens, you use the best approximation for how materials will behave rather than like an exact approximation. So when we think about the safety of a material, we have to also consider whether or not that material is of a low quality or a high quality. And quality is referring to whether or not that material is going to behave as we expect. So steel is a material that we can have a lot of control over. It's a homogeneous liquid that we mix various alloys and elements into it to make sure that it has the properties that we want, and we can make sure that it's consistent so that the outcome, we know that it's going to behave in a certain way. And that applies to aluminium and also engineered wood products. Concrete can have a lot of variables in it. Even though it's a liquid, it can be affected more by like air humidity and various other things while it's getting poured, hence why we end up with things like concrete cancer. And so that's considered like a medium quality material. And then dimensional timber, which is just any normal timber product that hasn't been engineered. So like as you go buy a 2x4 style plank of wood from a hardware store, that would be dimensional timber. We don't know what's inside that timber. We can cut a young tree down and be fairly certain that it doesn't have timber rot or knots in it, but the only way to find out is actually to cut it or do an x-ray on it, and so we can't be guaranteed to know how it will perform to 100%. And the same applies to earth and soil. So wherever we put our building, we can do spot surveys to see what's under the ground, but there could be a massive cavity under there that could cause an issue, and all we have to do is miss that cavity while we're doing our surveys, and you've got a catastrophic structural failure. So we have to assume that things that we can't necessarily control are of a lower quality, and we have to factor in for that. So loads are then basically magnified whenever we work with this stuff based on whether or not we think things are going to be predictable or unpredictable. So dead loads, we typically multiply dead loads by 1.2. We typically multiply live loads by 1.5. And then wind and seismic loads, it's calculated based on some weird functions. We don't have to worry about that too much. But if you factor all of those things in, then, if we've got a live load getting applied to a dimensional timber structure, then we might want to be timesing that live load force by 2 to work out what the size of all of the elements need to be. I've got to be really quick. So, is anyone's minds blown? No? Good. Was that didn't give you much chance to answer. Was that reasonably simple explanation for you guys? Did everyone follow along? Excellent. Okay, so we move on to our tutorial, and it's kind of in the tutorial that I was going to explain the assignments. So, and maybe even the course. Okay, so now if we just get into this course. So we've got 3 assignments. We've got 9 weeks to complete those assignments, okay? Because you guys have got, we've got 9 contact weeks to complete those assignments, and we've only got really 2 hours to do tutorials. So soon, eventually our lectures are just going to turn into sort of like semi-tutorials, sort of midway through, where the lecture will basically just be some coding that you guys can follow along. The first exercises were usually, you guys would be put in groups of 3, and you would have to have purchased a 3 mil thick plank of balsa wood and be asked to build a bridge of a certain length, and with the idea that that bridge would be broken by the end of the tutorial. Now, usually with that plank of balsa, we were seeing bridges that were, getting to about a meter. Was it about a meter long, Will?
Oh, you can get some crazy long ones.
Yeah.
People made them like 4 meters long.
Yeah, we got some really long bridges. But the thing is, I suspect, most of you guys don't have 4 meters to build a bridge in your apartments or houses or whatever. I certainly don't. So we've had to change it to pasta. And pasta's a really crappy material, to be honest, because it's very flexible until, like, it just doesn't have any ductility, really. It's quite brittle, but it's got a really good elasticity. And it doesn't really, there isn't really a structural material that we use in architecture that works similarly to pasta. It's just really bad, right? But the thing is, it doesn't matter too much, because we actually want to build something today that fails, because in a few weeks' time, after we've covered a few more structural concepts, you guys are going to have another go at designing this bridge and making it better, okay? So don't worry too much about making a good bridge today. The thing that you need to do well is analyze that bridge. So don't freak out. Now, has anyone not got pasta or noodles? Okay, everyone's got some pasta. And everyone's got the glue, all of the other stuff. The critical thing is we want to break this pasta. So, without really getting too deep into it, what we want to do...
So one of my issues is that I don't really have any decent glue. I just have the normal glue.
Normal glue? What do you mean? What's normal glue?
Like the sticks, the what's it called? Yeah, I just don't have hot glue or anything.
Pardon? You don't have hot glue?
Yeah,
What glue do you have?
The glue they use for paper.
Okay. Could you say what type of glue it is? Because
the glue, glue sticks.
Glue sticks. Okay. Yeah, that's awful glue. Okay.
Yeah, exactly.
Do you have sticky tape or masking tape?
Yeah.
Okay, you can use that instead.
Okay, cool.
Okay. So the thing is, a bridge normally a bridge would be something that spans between 2 points, and there'd be some kind of thing underneath it that you're trying to avoid. We don't need to actually worry about that too much today, other than whether or not something is going to break. So a good idea would be we want to design something that I don't care how much pasta you use. Okay, you can use as much pasta as you want, but if you do go excessively with your pasta, if we say, hey, let's just grab all this pasta and glue it together to end up making a mega bean, then what you're doing is you're actually wasting material. Oops, sorry, you can't see that. You're wasting material, because you could probably have achieved that same beam with 3 pieces of pasta. So if you're going to be excessive with your pasta today, then I would ask you to weigh your structure before we break it. Okay? So, or at least, just measure how much pasta you've actually used. So, look, here's 1, 2, 3, 4, 5, 6 strands, like if we say limit it to 6 strands, then that's also a fine exercise. What I would like you to do is design a reasonably sized bridge that spans, and if you want to make it 2 times the length of your longest pasta strands, that's going to make it a little bit of a challenge for you, because you can't just put one there. You're going to have to join them together. And the critical thing is, if you've got something like a book or books that you can put the bridge between, then that's going to make it easier for you to break, because you're going to put weights on that bridge and break it. If you don't have something that can lift it up off your table, then you're going to have to use the pasta to do that. So you can basically create feet. Can you guys see that? Create feet, and then those feet end up becoming the thing that lifts the pasta off the table. Okay? And really, when we're not going nuts, like if you end up with a something you're not satisfied with by the end of the 2 hours, don't worry about it. Let's just break it anyway and see how it goes. This is purely an exercise to give you something to do for your assignment. Okay? So what we're gonna do? Should we just get going? I'm gonna maybe make a breakout room for. Shall we make 2 breakout rooms? So if you want to have a chat, like if you want to throw some ideas about what you want to do with your bridge to me or Will, then just jump into these rooms. Can I ask you guys to can you turn your cameras on? Is that possible? Is it possible? Like I used to be able to look over a classroom and watch everyone like building their bridges, and it was good, but at the moment all I can see is Zinyi. Thanks, Zinyi, for having your camera on. So yeah, if you've got any questions about how to build this stuff, ask me and Will. Otherwise, I kind of want to just talk to you guys and find out, who you are, what you're planning on doing with computational design, and understanding, maybe how maybe hectic the last 2 terms were, because I know they were a bit hectic. So, and working out whether or not, what we can do this term, what you've had issues with previously, so we can cover them over the next 10 weeks. Cool. And look, if you don't finish building a bridge by the end of the 2 hours, then you've obviously got till next week to finish it, right? So if someone doesn't have any questions, then I guess just to start off with, Zinyi, do you want to have a chat in room 1? So you're at the top of my list.
Wait, it's top of your list.
You're at the top of my list, as in I have a list of all the students, and you're at the top. I'm going to try and build one of these bridges as well, by the way. So I'm going to get some glue.
I just wanted to ask, do we have to use like the whole pasta stick in its like whole entirety then? Or like, are we allowed to break it?
You're allowed to break it. That's what the scissors are for.
Oh, okay.
So just imagine this like you're building a bridge out of steel. It's just really shitty steel, right? So, I've got 2 bits of pasta and I've just snapped them. I can measure something out. So, like if I want to make a truss. So there's the beginnings of a truss, right? It might be worth me like gluing that in place and then breaking off the excess,
Right.
Just, yeah. And the thing is, because it's pasta, you'll probably find that things will break apart more often than what you want. So scissors will help. Cool. I know this seems like a like a high school physics exercise, but it's because we have to use it's because of this COVID thing. The bolster exercise was much seemed much more professional. Cool.
Are we taking strength to weight ratio?
Pardon?
Are we taking strength to weight ratio into account?
Yeah. So if you weigh your bridge at the end before you break it,
Yeah.
then you can then work out your strength to weight ratio for your bridge.
Right. Okay.
Okay, because we're going to don't think of the strength to weight ratio of just an individual pastor piece. But if you want, if you've got time and you've built a particular component and you want to test it breaking prior to actually using it, then go for it. Weigh it, test its strength. Also, just as a reminder, you should be taking photos all the way through, because that'll help you with the assignment. You'll have stuff to talk about. And critical thing is try and photo and video you breaking the bridge. That'll help you a lot because you'll see where it's failing. Cool. I'm going to stop recording just so whatever we say from now on doesn't get put up on YouTube, right? You can say whatever you want.